This is Inchara from Sri Venkateshwara College of Engineering under the Department of Computer Science and Engineering in Cyber Security. Today, I am here to give a brief information about addressing modes and flip-flops. The various formats of representing operand in an instruction or location of an operand is called addressing mode. Few types of addressing modes are register addressing, direct addressing, immediate addressing, indirect addressing, auto increment addressing, and auto decrement addressing. Register addressing. In this mode, operands are stored in the registers of CPU. The name of the register is directly specified in the instruction. Example, move R1, R2, where R1 and R2 are the source and destination registers respectively. This instruction transfers 32 bits of data from R1 register into R2 register. This instruction does not refer memory for operands. The operands are directly available in the registers. Direct addressing. It is also called as absolute addressing mode. In this addressing mode, operands are stored in the memory locations. The name of the memory location is directly specified in the location. Move location A, R1, where location A is the memory location and R1 is the register. This instruction transfers 32 bits of data from memory location A into general purpose register R1. Immediate addressing. In this addressing mode, operands are directly specified in the instruction. The source field is used to represent the operands. The operands are represented by hash sign. Example, move hash 23, R0. Relative addressing mode. In this addressing mode, EA of an operand is computed by the index addressing mode. This addressing mode uses PC to store the EA of the next instruction instead of GPR. The symbolic representation of this mode is X of PC, where X is the offset value and PC is the program counter to store the address of the next instruction to be executed. Auto increment addressing mode. In this addressing mode, EA of an operand is stored in the one of the GPR of the CPU. This addressing mode increment the contents of the register to point the next memory locations after operand access. In 32-bit machine, it points to the next memory location by adding 4 to the current location value. The symbolic representation is R1 plus, where Ri is one of the GPR. Example, move R1 plus, R2. This instruction transfers data from the memory location whose address is stored in R1 into R2 register, and then it increments the contents of R1 to point to next address. Auto decrement addressing mode. In this addressing mode, EA of an operand is stored in one of the GPRs of the CPU. This addressing mode decrements the contents of the register to point to previous memory locations after operand access. In 32-bit machine, it points to the previous memory location by subtracting 4 from current location value. The symbolic representation is minus Ri, where Ri is one of the GPR. Example, move minus R1, R2. This instruction first decrements the contents of R1 by 4 memory locations and then transfers the data of that location to destination register. Storage element flip-flops. A flip-flop in digital electronics is a circuit with two stable states that can be used to store binary data. The stored data can be changed by applying varying inputs. Flip-flops and latches are fundamental building blocks of digital electronic systems used in computers, communication, and many other types of systems. Both are used as data storage elements. It is the basic storage element in sequential logic. It is a synchronous circuit and is also known as gated or clocked SR latch. There are basically four types of flip-flops in digital electronics: SR flip-flop, JK flip-flop, D flip-flop, and T flip-flop. SR flip-flop. This is the most common flip-flop among all. This simple flip-flop circuit has a set input and a reset input in the system. When you set S as active, the output Q would be high and Q dash would be low. Once the outputs are established, the wiring of the circuit is maintained until S or R go high or power is turned off. As shown below, it is the simplest and easiest to understand. The two outputs as shown above are the inverse of each other. The truth table of SR flip-flop is highlighted below. We can see if Q is 0, Q bar is 1, else Q is 1, Q bar is 0. JK flip-flop. Due to the undefined state in the SR flip-flop, another flip-flop is required in electronics. The JK flip-flop is an improvement on the SR flip-flop where S is equal to R is equal to 1 is not a problem. The input condition of J is equal to K is equal to 1 gives an output inverting the output state. However, the outputs are the same when one tests the circuit practically. In simple words, if J and K data input are different, then the output Q takes the value of J at the next clock edge. If J and K are both low, then no change occurs. If J and K are both high at the clock edge, then the output will toggle from one state to the other. JK flip-flops can function as set or reset flip-flops. D flip-flop. D flip-flop is a better alternative that is very popular with digital electronics. They are commonly used for counters and shift registers and input synchronization. In the D flip-flop, the output can only be changed at the clock edge, and if the input changes at other times, the output will be unaffected. The change of the state of the output is dependent on the rising edge of the clock. The output Q is the same as input and can only change at negative edge of the clock. T flip-flop. A T flip-flop is like a JK flip-flop. These are basically single input versions of JK flip-flops. This modified form of JK is obtained by connecting inputs J and K together. It has only one input along with the clock input. These flip-flops are called T flip-flops because of their ability to complement their state. Hence, they are named toggle flip-flops. Thank you.